This is the Aftermarket Radio Network.
Welcome, everyone, to yet another episode of Diagnosing the Aftermarket A to Z. Today, I would like to talk about breaking down and kind of analyzing the voltage and current patterns to simple inductors. But first, I'd like to mention our sponsor, NAPA AutoCare. Since its launch in 2020, the NAPA AutoCare member site has continued to evolve to keep members updated on all the NAPA programs, promotions, benefits, and other information available to help their businesses thrive. If you are a NAPA AutoCare member, visit member.napaautocare.com to access the member portal. Not a NAPA AutoCare center? Contact your servicing NAPA Auto Parts store to learn more about how to join the NAPA family. All right, so I guess I thought it would be kind of cool to walk through a couple of waveforms, kind of thinking about it. I think the easiest way to kind of do this is recommending you download some free software for the sake of navigation and hopefully just ease. I would have you go to the Pico Auto website, so www.picoauto.com, and download the Pico 7 software. I think that'll be the easiest way to do this. You can, of course, use anything you have to pull up a inductor voltage waveform. So not to speak in a way that's being evasive or anything like that. When we think of an inductor, we should be thinking of coils of wire, and namely solenoids, coils like ignition coils. Those would be inductors. The most common that when we're looking at these waveforms that probably comes up is a fuel injector, the saturated switch style fuel injector. When you get the Pico Auto software downloaded, Pico 7, open that up and it's going to kind of come up with a dialog that says connect device. And in this case, we won't want a scope plugged in. And if you don't have a scope, great. You're going to see something called available, and below that it'll say demo. Just make sure that's highlighted, and then just to the right, click OK. It'll open up another dialog, but behind that, the scope will open and we should see some patterns flying around. We can X out of that dialog with the automotive testing with Pico scope. You should see a blue trace going and then a red trace. To make it a little bit easier on the eyes, to the top left, you're going to see the letter A and the letter B. For the letter A, left click on the plus mark. That'll change our voltage range. It'll increase the voltage range. It'll put more voltage on our screen. And maybe click it one more time. So you'll have 100 volts plus or minus. And then just below that will be the letter B. And for fun, if you want, we can start hitting the negative sign, the minus sign for channel B in red. Left click that minus sign a few times. Maybe get her down to, 200 millivolts, plus or minus 200 millivolts. And you'll see a waveform now. But they're kind of laying over the top of one another, and it'll make it a little hard to look at. So if you would like, you can left click and hold right on the blue voltage scales. So where it says 0, 20, 40, 60. If you hover over that with your pointer or your mouse, you'll see that kind of turns a black arrow with a pointing up and pointing down. Left click and drag that down. And you might notice in that scale, as you're dragging that down, a thin blue line. That is our 0 line. I typically like to line this up with not the very bottom, but one division up from the very bottom. And so my 0 is on that second from the bottom grid. And now my traces on my screen are separated. I have the blue on the bottom, the red on the top, and they're kind of screaming across my screen. We can handle this a couple different ways. The first thing I think we should do is go up to the very top and kind of to the left next to where it says running. It'll say time base. And I think we're going to speed the scope up. We're going to put less time on the screen. So we're going to left click on that minus sign. And we'll probably notice that those waveforms are getting a little bit wider. And let's just say 500 microseconds, or it'll look kind of like a 500 with a backwards letter Y and S/division. So that'll be microseconds, 500 microseconds per division. And it's going to be very hard to see this trace. It's just screaming along. The next thing we're going to want to do is just to the right of time base, you'll see trigger. And I just want you to hit the plus sign. And that'll set it up to be a very simple edge trigger, auto. And we're just going to hit that plus sign a couple of times. You know, I have mine set up a ways to like 40 volts. And now that pattern will be jiggling, but it'll be fairly stable. At least enough for us to analyze. And if we really wanted to, we could just hit that space bar and that will freeze the scope. And that'll be good for an analysis standpoint, I think, at least for the purposes of this episode. Now, what we're looking at is a solenoid. And I think we'll get into this a little bit later as to why we know it's a solenoid, meaning that we have a coil of wire, we have an inductor, not unlike an ignition coil, but the center portion, that ferrous material moves, or that wouldn't happen in just a pure inductor or like an ignition coil. So let's start with the channel A, the blue trace. That's voltage. Looking at this left to right, you're going to see that our voltage is sitting a little bit below 20 volts. And if we really wanted to, you could left click. So set your pointer right on that blue line, pointing at that blue line. You could left click and a little dialog will pop up and you'll see time at the very top, but then you'll see A : and mine, the way I hit it by accident is 14 volts. Yours might be a little bit higher, a little bit lower, depending on where you situated that pointer. And that's our voltage really feeding this inductor. Now let's talk about a little bit where our leads would be placed. So we're looking at this as a software generated waveform, but let's think about where our leads would be placed. On our scopes, we would have a test lead connected to channel A, a blue lead and a black lead to that one channel. The black lead is most likely going to be connected to battery negative or something that is going to represent ground or earth. That is going to be our reference. So you can kind of think about scopes and meters as calculators that they subtract from one another. Assuming our black lead is connected to battery negative, that blue lead, or in some cases, if we're talking about just a regular meter, it might be red. If we're using a snap-on scope, it might be yellow. This lead is going to be on the control side of this inductor, be it a fuel injector, a shift solenoid, a purge solenoid, a vent solenoid, something of that nature. We're on the control side, not the side that's feeding power from, say, a fuse or a relay, but the side that's going to most likely a control module of some sort. If it's a fuel injector, it's most likely going back to the engine control module. That's where our lead is going to be placed, either back probing, piercing, however we're going to access that wire and that circuit. So we're seeing this voltage kind of through the inductor. We'll probably just keep referencing this as a fuel injector, probably just make it easier to think about, picture in our heads. With the key on, engine off, or the engine running, we expect that voltage to be there most of the time. If it's never there, we would move our lead to the other side. It's going to be two wires. We're going to move it to the other side. Do we have power there? Do we have it all the time? Does it ever drop? That would be a very quick test, easy test to verify that power is getting to that injector. In this case, we can see it's there. So we're going to be on that control side. And over a ways, we see it go from 14 volts or system voltage down close to zero. Is it going to be actually zero? No. It's going to be very close though. And that's where the driver or the transistor in that control module is pulling that low. We can say it's pulling it to ground. We can say it's pulling it to zero, but if we really want to be nitpicky, it's not pulling it to all the way to zero, but it is definitely pulling it low. The purposes of which is to allow current to flow. And when we have current flowing, we start building up a magnetic field. The purposes of that magnetic field, of course, are to open that pintle. So we have it pull low. It's holding it there for a while. And we drift over a little bit further. And if we really didn't mess around with our pre-trigger, that trigger diamond is going to be right around 0 or right at 0 for time. So if we're looking at that bottom scale, probably see a 0. And we see a spike of voltage. This is known as the inductive spike or the inductive kick. It's a very, very important characteristic of inductors because there is only one way we develop that spike, and that's because a magnetic field was created. So that makes it kind of a powerful diagnostic tool, or at least analysis point. We do not get an inductive kick without a magnetic field. So if we have 50, 60, 80, 100, if we're talking about ignition coils, 400, a couple hundred volts, we know we built a magnetic field. The only way we build a magnetic field is if we have current flow. So that's proof that current flowed. And if we have an idea of what that voltage should be, that where that inductive kick will hit, then we know we have current flow. We know we have circuit integrity. And, at least for current flow characteristics, that we're flowing the right amount of current. We can't really have bad connections. We probably don't have voltage drop across relay contacts or across a fuse or a bad connection at the injector. We're flowing enough current to build up that magnetic field. It collapses. We get the inductive kick. So it's a good characteristic to pay attention to. Note, maybe build up a database either in your brain or through saved waveforms or notes, what you would expect to see. Some engine platforms, you can pretty much make that a specification. We probably won't find it in service information. You're going to have to build your own, but it is going to have to hit that point, and you can record that and make that something to look at regularly. It's no secret we're facing a technician shortage. NAPA Auto Care has a solution with the NAPA Auto Care Apprentice Program. The program was engineered by one of our own. Pete McNeil and Master Technician Jake Sorensen of McNeil's Auto Care in Sandy, Utah realized that the problem of not having technicians available for hire was not going to solve itself and decided to take action and look at a different audience of individuals available for hire. A focus was put on younger individuals with the right passion, desire, and attitude to work in the automotive repair industry. Jake and Pete sought these individuals and developed a technician apprentice program to give them the training needed to become a successful technician in today's world. The NAPA Auto Care Apprentice Program includes a comprehensive 9-stage curriculum that includes a variety of types of training, classroom training videos. Exclusive to the apprentice program, these videos provide an in-depth training from a successful master technician, auto tech classes, instructor-led courses offered through NAPA Auto Tech e-learning, web-based e-learnings designed to target specific training topics, hands-on learning. The apprentice will apply the skills gained from the classroom training videos, AutoTech instructor-led training, and AutoTech e-learnings in the shop with the guidance of a mentor. The apprentice program curriculum is competency-based, meaning an apprentice can move through each stage at a pace that best suits them. Most apprentices complete the program within 2 years. Upon completion, apprentices will have earned ASE G1, A4, A5, and AC certifications, adding industry validation to the skills an apprentice acquires. Grow your bottom line. Having an apprentice in your shop will ultimately benefit your bottom line as they advance through the program. In most cases, as the apprentice develops their skill set producing billable hours, you will begin to see a growth in your gross profit by stage 5. Keep your apprentice motivated with an apprentice toolkit. One of the largest entry barriers for individuals looking to enter the automotive repair industry is the cost of tools. NAPA Auto Care has worked with our supplying partners to offer an exclusive, comprehensive tool set, including a 4-drawer tool cart for all registered apprentices. To learn more, members can visit member.napaautocare.com. Now, as we keep moving to the right of this waveform, the voltage has kind of hit a peak. In our case, it almost looks like it levels off a little bit and then starts dropping. Technically, all of them will do that, just depending on time base. I mean, if we really zoom in on stuff, things don't happen instantaneously. So we're going to see this voltage start dropping, and it's dropping and it's dropping, and then it kind of levels off and drops again. So we kind of have this bump, if you will, and it is most often referred to as the pintle bump. It is a characteristic that we do look for because it's important depending on the inductor we're talking about. So in this case, we're talking about a fuel injector. We could be talking about a shift solenoid, again, purge solenoid, evap vent solenoid. We want some representation of mechanical movement. Is that pintle moving? If that voltage was dropping down, and it was all nice and smooth, we have to start considering that maybe that pintle didn't move. So if we're chasing a misfire, so it's misfiring on this cylinder, and we verified we have spark, we haven't, maybe relative compression is good. So we back probe that injector and it's nice and smooth all the way down. We could consider that maybe that fuel injector is stuck. It is not opening, or it's stuck open. What's nice about most cars is we have other cylinders or other components to reference. So if we have a 4-cylinder here, we're looking at a fuel injector. We have 3 others to kind of compare to. Some fuel injectors, the pintle bump is very, very pronounced, and some other platforms, not so much. Doesn't necessarily jump out at you. Sometimes we have to mess around with our settings to better focus on it. Sometimes it's just a characteristic of the inductor itself that it just does not have a pronounced pintle bump. The reality is we know that we have mechanical movement because if you think about it, that pintle's a ferrous material. If we move a ferrous material through a magnetic field, we do something, right? We change the inductance. We could be creating a voltage. Something changes. That's what we're seeing there. That's why we can say that that is mechanical movement, and that's proof of it. And after that, we see it level off again, and that's our system voltage. That is a very typical analysis of a solenoid, really, on almost any car. It could get a little backwards if we have a positive side switched solenoid, but the reality is these basic components are all pretty much the same, regardless of year, make, model. So this can be kind of a universal thing. Now to the red trace, channel B. That is representing current. So we have presumably a inductive current probe, a current clamp around the feed or the control wire. Doesn't matter which. Current's the same. One thing we might have a little bit of heartburn with is we're looking at this in voltage. So those of us that use current probes regularly probably are just doing the math in our heads. We're not setting up the scope to read in amperage. Most low amp current probes read 100 millivolts per amp. So, again, using our left click trick, we could left click on this and see that we're at about 100 millivolts, and that would represent 1 amp, which on many saturated switch style fuel injectors, that is a very normal reading, 1 amp at the peak, at that kind of that hold section at the very top of the current waveform. And if we want, we can come over to the far left there, that far left column, left click inside the white portion of channel B. Just left click in there. That's going to open up our channel options for channel B. And right along the top, you're going to see vertical and then probes. If we left click on probes, we're going to see that it's, highlighted in blue ×1, which would be just a regular test lead. Just below that, we got some choices for current clamps. And honestly, we could just pick the first one, the first 30 amp one. And now, if you just left click anywhere on the scope screen itself, you're going to see that we have now changed our voltage ranges, or the scales, I should say. The voltage scales are now reading in current and amps. So that may make things a little bit easier on the eyes, a little bit easier for processing. And let's kind of just look at this current waveform. Generally, we're going to see this pretty close to 0, starting off to the far left. It's going to be reading pretty close to 0 unless this circuit is also feeding other things. So, I kind of said we're going to have the current probe around the feed or the control. We're thinking right at the injector. We're probably going to see this pretty close to zero. If not, the probe probably was not zeroed, or, in the case of what we're looking at on our screen, that probe could have been located, at a fuse, who knows where, further up the circuit where it's feeding more than just the fuel injector itself. So generally, we're going to see that very low, close to zero. Could use the probe, could have been zeroed better. Or sometimes if you have what looks like current when there's no current, sometimes just snapping the jaws open and shut, just letting that spring-loaded tension snap those jaws shut a couple times helps eliminate that. So first thing we're seeing is where the blue trace drops to zero or close to zero, we're seeing the current start rising. So we're flowing current. We've completed the circuit. Current is flowing and it's not jumping straight up. The reason it doesn't jump straight up is because this is an inductor. We have something called inductive reactance. It's working against flowing current to build this magnetic field. As it's building, we're seeing some changes. Like it's rising rather slowly, then it kind of speeds up. The angle gets a little bit steeper. And then further up, we see another change. And this is where sometimes analysis isn't always really pronounced or just really obvious. We could have that pinhole opening further down, maybe a quarter of the way up, or we might be looking at it a little bit more closer to the top, and then maybe that last 75% range of that rise. So from where it goes from close to zero to where it's kind of saturated at the top, where it flattens out on top, we could see evidence of that pintle opening. Now, you might be asking yourself, could we see that in the voltage? So if we're back straight down on that blue trace in that hold section, could we see this? And on higher resolution lab scopes, a lot of times you can. A lot of times if we zoom in really close, really tight on that hold section, you'll basically see a reflection of current at the bottom. And you can see the pintle bump if you like. Usually it takes a very high resolution scope. And by that I mean, 12-bit, 14-bit, 16-bit scopes. The higher the resolution, usually the better they show that off. But usually we end up analyzing it like this. At the voltage waveform, we've had evidence of a pintle bump during closing. So for it to close like that, it had to open. In current, we typically see that reflection or indication of mechanical movement on the rising side as the current is rising. And just like I was saying with the voltage trace, that pintle bump, sometimes it's really, really pronounced. And sometimes like this one, it isn't so much pronounced. So luckily we have the voltage waveform that proves that we had mechanical movement, that pintle's moving. We get to the top of the waveform current. It's kind of flattened out. That's when it's saturated. It's flowing as much current through it as it's going to flow. Usually we're going to expect that to be easily calculated using Ohm's law. So if we have a 12 ohm or maybe better yet, a 14 ohm injector, if we take a resistance test of this injector and it's 14 ohms and we're running 14 volts, we would expect 1 amp, right? So that's where we're going to expect that peak to happen. And then as we keep growing across to the back end, we see the current drop as that inductive kick occurs. We're watching the magnetic field collapse. We're not flowing current through anymore. And then we're kind of back down to that zero range, that low level of current that we're going to expect to be pretty close to zero. So that's really just the basics of looking at an inductor. I think next time we'll look at another type of inductor, ignition coils, where we have a little bit more going on, not in movement, but we have mutual inductors. We could think about coils as being transformers and not like Bumblebee or Optimus Prime, voltage transformers, step up transformers. So thank you very much for listening. I really appreciate all the feedback you guys have been sending. If you are listening to this on YouTube, please hit the like button and the little bell to alert you when new episodes come out. I'd really like to thank NAPA Auto Care for sponsoring, and Aftermarket Radio Network for making this all possible. And you know what? While I'm mentioning the Aftermarket Radio Network, I have to really give a shout out to a fellow Aftermarket Radio Network podcaster, Hunt Demarest. He has a podcast called Business by the Numbers, and episode 44, he just really released it a few days ago. He did Talking Numbers with Frank Skandura. Frank Skandura owns a repair shop in Las Vegas. I think they specialize in European cars. I kid you not. I really kid you not. This is must listen. This is a must listen for anybody and everybody that works in an auto repair shop. It doesn't matter if you're a manager. It doesn't matter if you're a service advisor. It doesn't matter if you're a technician. It doesn't matter if you're on the lube rack or if you're the heavy line shop foreman. It really is an hour of your time very well spent. I listened to it twice in a row. It just really resonates with me, a lot of what they're saying. And I think that it would do anybody and everybody a lot of good to hear what they're talking about. So if you have any ideas, any questions, please don't hesitate to ask. You can reach me on social media, or you can email me at mattfonslowpodcast@gmail.com. And until next time, take care.
You've been listening to Matt Fonslow, diagnosing the aftermarket A to Z on the Aftermarket Radio Network. Follow Matt on your favorite listening app. He's very interested in what you have to say. Let him know what you'd like him to cover and come on the show. Matt is all for advancing the aftermarket. Find Matt Fonslow on social media and connect, or on aftermarketradionetwork.com.